Good morning, everybody. So let us start our lecture today. Today is November 11. Okay, 11/11/21. Okay, as we see our schedule, so we are at the end of the semester. So we have just 2 more weeks, and actually we have one more topic to discuss: graph algorithms, graph data structure actually. And then after the break, we will discuss some advanced sorting algorithms if we get some time, or we'll review. Okay, so in our last lecture we are discussing hash tables and hashing. Okay, so hashing is used for searching purpose, right? As we learned in our last lecture, hashing is used for searching purpose. For instance, we know the linear search algorithm, the linear search process for an array that elements are put together in a linear array, and then we search one by one. So, and then we discuss so others like binaries, BST, binary search tree. That is, elements are structured in tree type, and we also know that other data structure, for instance, sorting, for instance, binary, what is that called? Heap sort we discussed, right? So linear search algorithm, so it goes one by one. Okay, and then binary search algorithms, it splits our data set every time into two halves, and we throw out another one half and we consider one half. So every time data set is shrinked by half, so this is why it is called binary search. By means two, so either we take either of the two sides, and then searching efficiency is better in binary search algorithm. It takes log n time with base 2, but one of the limitation of binary search algorithm is that we know that data needs to be pre-sorted, and we know that all sorting algorithms take larger time than searching algorithm. In the worst case, searching algorithm takes big O n, right? So if the number of elements exist, we may need to go all the way and searching one by one. Okay. We also know that we also discussed linked list, right? So linked list, we need to go through one by one. So in that case, big O n. So that searching in the worst case, complexity or efficiency is big O n. Okay, but for linear searching, and we saw that in BST, in the worst case, it is big O n, but in a balanced tree, it is log n, big O of log n, and in binary search algorithm, it is big O log n. Okay, in the best case linear search algorithm is big O 1. 1 means constant. Okay, but we want to develop a searching process that it takes always constant time. Okay, so that is the process of this. Okay, hashing. So as hash table is used to make the searching process easier or efficient, so that it can be searched in constant time or pretty close to constant time. Okay, so that hashing algorithms, our efficiency, our searching efficiency is pretty constant. Okay, that means for any item we want to hash, we want to search, it gets equal amount of time. It does not matter how many elements I do have in my hash table. So what is the process of hashing is that the elements or the items we want to keep in a table. So hash table is a table. It is organized as a linear array. Okay, or the simple array. Okay. So each item constant is key and value. Key, for instance, in dictionary, we are familiar with dictionary like book, paper copy dictionary, right? So it has the word that is key and the definition or uses of the word is value. Okay, so it is assumed that in a hash table, all key will have single index key, unique index. In an array, elements are searched with index, right? 0, 1, 2, 3, 4. And this in hash table, these index are calculated from the key itself. Okay, so this is in this technique, key is used, okay, to generate it is associated index value in the table. So that means the hash table, it is not like the dictionary, regular dictionary, language dictionary, that our words are sorted, are already sorted in ascending order. It does not need to be sorted. Okay, it will be sorted based on the hash value of the key. Okay, and then in our last lecture we discussed that how do we generate index from the key value. Okay, for instance, the simple way, for instance, key values, these are our key values are, for instance, our values are some numeric numbers. Okay, then there are several ways. One of the ways is that we use a function. This is called hash function. So x is a key or whatever we say, and then we discussed that in our last lecture that we use some mathematical function to generate keys. Okay, for instance, in our last lecture we discussed that. Give me 1 second, please. If we have a given data set, in our last lecture we discussed that if we have a given data set and we use modular operation to generate the corresponding index, okay, using modulus operation. Okay, and for instance, and then we use modulus operation and then m, right? We use m. What is the m? We say that m is the nearest larger prime number. This is m is a prime number that is nearest larger prime numbers than the number of items. Okay, so m could be 13 or m could be 31, it could be 11, whatever we like. Okay, for instance, if our key value is 35 and then m is 11, so then we use 35 mod 11, that is mod is used for find the remainder modulo operation, right? So 33 divided by 11, how many times is go? 3 times. 3 times 33 equal to 30. 3 times 11 equal to 33 plus 2 equal to 35. So 2 is the remainder. So we will use this 2 as the index in our hash table. But sometime we may see that we may get for a large number or for some numbers we may get same remainder or index value for multiple numbers. For instance, if m equal to 31 and if we have our key or the key values, okay, and then we see if we do modulus operation 1000 with 31, then we will see that we will get key remainder 9, 8. Then for 1001, 9, for 1002, 10, and so on. Now, if you have other numbers, we know that if our number is 1000, 2302, and then it generates with same M, it generates the same key. So for this set, it generates same key, so that we are getting some duplicate key values, right? So in order to resolve these duplicates, we say this problem is that called collision. So whenever is collision, there are some ways to detect collision, to resolve this collision. Okay, one of the process is called open addressing. In open addressing, we find the free location, nearest free location, next free location, and we put our items in that location. Is another way is called chaining. Chaining is the way to use another data structure on that position where the collision occurs, like linked list. Okay, for instance, here so for instance, key value is, for instance, this one. So okay, so open addressing means, what is the process in open addressing? That we find the nearest or next available location to put our value. So there are multiple open addressing process. One is called linear probing. Linear means one by one, right? Okay. So in the linear probing, the search of an empty location used to following sequence for a hash tables. For instance, this is used, for instance, the next location d plus 1, d plus 2, d plus 3, dot m minus 1. And what is the d value? D is maximum the m minus 1. D gets the value maximum m minus 1. Okay. And then whenever we do linear probing, something we count, another thing, important thing, is called number of probes. Number of probes is that for a given key, the number of checks item. That means how many times we are checking for the next location, how many tries we are giving to find a suitable location or an available location for a key to be placed. So this kind, in this process, number of probes value is also saved to be used for retrieving the value from the table. So if you use probe, then we need to save this probe value to retrieve that value. So whatever we are saving in our hash table. So let us see today with this, we will see something that how do we use linear probing, and then we'll see there quadratic probing. Okay. Or there is also dual hashing, so you will see some examples. Okay. What is the data set? This is from the book. You can read it. Let me give you an example. That is easy. We will come back here later, but let me give an example. Simple example that. Okay. quadratic probing, double hashing, chain hashing. Okay. Actually, I have another slide from you will learn more about hashing in algorithm analysis course. So I have a slide from algorithm analysis course. Let me open that slide. So I have my own slide from algorithm analysis. Let me go it from here, then you will understand easily. Then we can come back over there later. Okay. So in hashing, we use a hash function, right? For instance, this is in hashing. These are the numbers, keys, K1, K2, K3, K4, K5. We need to put this in a new hash table, for instance, in a new data structure, in a new array, so that we can search any of these keys in constant time, right? This is our goal, right? Okay, so we use hash function. So the function is, for instance, h. Okay, so h of k hash function. For instance, if we h of k1, it will generate this one, and we will put this value. Okay, so let us see some examples. So we said that collision when it happens. So then we see we discuss the chaining. We use chaining. So let me give you some pretty simple example. Okay. So in order to develop a hash table, we need to select a good hash function. So hash function is our own choice. We will select our own hash function. Okay. So there are some good criteria. So one of the good criteria our target will be, we will be selecting a hash function that will generate unique key, unique index for each key, right? That is our goal, but we may not find always unique key, unique index value. So, but our goal will be that. So our goal will be to select a good hash function, okay, that generates unique keys. Okay, so a good hash function should be distribute the key uniformly into the slot of the table. That is the goal. That actually okay. So, but we know that we may not get this. So then we have our own way how to do that. So, for instance, a simple hash function. In our last lecture, we discussed that simple hash function is h of k equal to k mod m. So what is m? M is the nearest number, a prime number that is greater than, slightly greater than the number of elements. Okay, and for instance here. So let us see some examples. Okay. So m usually it should be prime number, but it is okay if you can even select a non-composite number, it may work, but the goal is that, for instance, we will select a prime number for m. Okay, so what is that on? Let me see. Okay. In our last lecture, we discussed that, for instance, we have a data set for instance, key set equal to maybe 13, 24, 7, 20, 25, 34, 26, whatever a number is, 1, 2, 3, 4, we will take 8, 27, 45, no matter. Okay, and then we use that, for instance, here we can say m equal to, the formula will be h of k equal to k mod m. Okay, so m here, m can be, we can say 1, 2, 3, 4, 5, 6, 7, 8, 9. So m, the number of elements over here 9, right? So what is the m value? We can say m, we can say 11. A prime number nearest to the number of elements. There are 8 or 9 numbers over here. The next prime number is 11. We could say 13 also, right? So then we will make a table. Okay. So table will have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So 0 to 10 equal to 11. Okay. We don't need the last one. 10 is fine. So 13. So 13 for the number, each of the number. Now each of the number will be entered into this hash function. Okay. So k 13 modulus 11 equal to 2. So 2 at the position of 2, index 2, that will be position 13. Okay, 24. So index 24, right? So 11 times 2, 22, and then 24 also is supposed to become over here. For now, let us put it over here, and let us think that we can put a linked list. 7 is modulus 7. 7 will be over here. Okay, 20 is modulus 9, so 20 will be here. 34 is 11 times 2, 33, 1, right? So 34 will be over here. And then 26 is 5, 11, 22, 4, right? So 26 will be here. And 27 so is modulus 27 modulus 11 equal to 5. So 27 will be here. And then 45 modulus 1, right? So 45 will be over here. Okay. So this is one way, for instance, there are some collisions over here. And what did we do? There are two ways that chaining. If we use another linked list over here, so we can put 24 next to 13, because 24 and 13, they have same index number. 13 modulus 11 equal to 2, 24 modulus 11 equal to 2. Similarly, 34 modulus 11 equal to 1, and 45 modulus 11 equal to 1. Okay, so if we put this way, so this is called chaining. Instead of chaining, what we can do open addressing to resolve collision. What is open addressing? Then we will be looking for the next available empty position. You see that in this table, there are some empty slots, right? So this is empty. this is empty, this is empty, this is empty, this is empty, and this is empty. So we know that we for sure that we put m as the nearest greater number, the largest number, than the number of elements. So definitely we will have some empty space. So now our goal will be, instead of making a chaining over here, what we want to do, we can find the next number, next available empty space. For instance, when we put 13 over here. Next, whenever we got 24, then we say that 24 position index is 2, but it is already occupied. So then what we'll do, we will go for either chaining, or we can look for next available open position. So then the question is that how do we find the next available open position? That is called open addressing. Okay, one of the simplest open addressing is that using another I index, another index I, so that is instead of using this hash function, we can use another hash function h of k equal to, okay, so h, so no, so not this one. We can use something like this, h of k plus I modulus m, and I will be 0 to 1 to 2 less than m minus 1. Okay, so the initial phase I equal to 0, and then if with I equal to 0 we do not find an empty space, then we will increase I for the next I, so I equal to 1. Okay, and sometimes this can be written as like that, is h dash k plus I modulus m. Okay, and what is it? So hk equal to h dash k plus I modulus m. So here I is a linear function. This is a linear function. Linear function or linear increment. This is why it is called linear probing. So here, for instance, whenever we encounter 24, so 24 modulus k 11 equal to 2, and then we see that hey, this position is already filled up. So then whenever we need to increase I. So I is initially I was 0, then we increase I by 1. So then I will be, so here 24. So that means this value will be 2 plus 1, 3. 3 modulus 11 will be 3. So then instead of putting 24 over here, we will put 24 over here. Okay, and in that case, we see the number of probe equal to, so that we initially we failed, we did not find an empty space. Now in the second try we get 1, so that number of probe equal to 1. Sorry, number of probe equal to, first time we did not get it, the second time we got it, number of probe equal to 2. Similarly, later whenever we put 45, we get 45. Okay, whenever we got 45, okay, so then we know that 45, it generates 45 mod 11 equal to 1. So this 45 position is already occupied. So then we increase I by 1. So then we got index 2. So okay, so that we see this position is already filled up. So then we increase I by 3. Then is this position already filled up. Okay, so then we increased I by 1. So then this position is already filled. This position is already filled, another. So until that, at some point, we will get position for 45. And then maybe probe will be 1, 2, 3, 4, 5. Probe will be 5. Probe is 5. That means whatever the initial value it comes, it does not get place over there. So if we add 1, 2, 3, 4, 5, 5 more. Instead of initial index, add 5 more, then you will get his position. Okay. Here maybe probe value would be 1. So if we say add 1, that should work. Probe value 1 should work over here. Yes. So for 24, we'll say probe value equal to 1. That means if whatever 24 first generates, it is not actually over there. It is one more step. Probe means one more step. Go to one more. Okay, and then 25 or 45, whatever it first generated is generated index. It is not there. It adds 5 more. Probe, that means it's 5 more steps it needs to get. So this is the way for probing linear hashing. So open addressing. In open addressing, what do? We find a nearest empty position for the key so that it takes place. So simple open addressing is called linear probing. So we use a linear function. And then I 0 to m minus 1. Okay, this is linear probing. So that means we increase I until we find an empty slot, and we should get an empty spot. And sometime in the rare case, we may not get an empty space for a number. It may occur same thing, same occupied position. So in that case, we say that value is that key is unsuccessful key. And then we may create another list for unsuccessful keys, but that is rare case. So at this position, does anyone has any question?
No questions.
Okay. So you understand the linear probing, right? Linear probing is the simplest one that increases the in I, okay, steps one by one. Can you hear me? Sorry, my computer is restarted suddenly, and then I joined on my phone. It is restarting. My computer is starting. It will take a minute, maybe. I don't know what happened. Can you hear me?
Yeah.
Sorry, my computer restarted suddenly. I do not know why. Now you see my screen, right?
Yep.
Okay. Yes. So, sorry, my computer restarted suddenly. I don't know why it happened. Maybe there was a what is called there was a system update, operating system update. Maybe not is better. Sorry, I don't have the previous drawing. Okay, so that's gone. Okay, so now we understand linear probing, right? With a simply modified method, modified function. So this is called linear probing. That means the next slot, okay, is search. Let me see if I find that. No, that is not available. So what we got over here, so we got our table. We saw that can anyone please help me to recall the table items? 4, 5, 6, 7, 8, 9, 10. So we have our set K equal to what is our set? K equal to first one was 13, right? Then 24, right? Something. like 7, and then maybe 18, maybe 20, and then sometimes there was 45, sometimes there was 26, 30, 35, or something like this. No problem. So whatever we saw, that 13 took place over here, right? 13 took place. 13 took place over here, and then 22, it was about to take place over here, but due to use of linear probing, so then we can push 24 from the next position. 24 is over here, and then 0. Maybe there was a number 22. So 22 take place over here. 23 took place over here. Okay, so then whenever 45 arrived, so whenever we see that before 45 this position were already occupied, so then 45 took place somewhere here in the down, right? So 45 came over here. So using linear probing, so we search one by one in this space. Okay, sometime and this way for somehow we get an empty space, an empty slot for a key, right? So this is for open hashing, open addressing. But you see that, did you realize that for some time, in order to get a position for 45 in previous example that discussed, we had to search a few times. The probe get 5, right? So that for some numbers, if there are a lot of numbers, sometimes maybe probe value is large. Probe value maybe, if m, for instance, for large numbers, m may be a very large number, a large prime number, maybe 1001 or something like this, if m equal to like this. And then probe maybe for long, for instance 990, probe value maybe 990. So in that case, that means we need to do some search, make some space, right? Make some time. So that is a slow process. So in order to resolve that process, there is another kind of probing, that is called, okay, one of the probing that is called quadratic probing. So in quadratic probing, the I value increases faster than instead of linearly. Okay, I values quadratic means I equal to 2, I squared. So for I, whenever I change from 1 to 2, then you see that 2 squared means 4 plus 2, 6. So it will jump with 6. For I changing 3, then 3 times 3, 9 plus 3, 11. So I will be changing faster. So this is called quadratic probing. So that means the jumping method, the initial part, is used as a different quadratic method. Okay, so this is called quadratic probing, and the process is same. For linear probing, now we remember that for linear probing, we use the function. Okay, for linear probing, okay, actually the hash function is written actually like h and I. The I is also independent variable, right? H of I equal to h of, for instance, k plus I and whole modulus M. Okay, for quadratic probing, you see that H quadratic probing is that H of I Ki K Ki equal to H dash K. We can say H K or H dash K, same thing. Okay, plus you can say C1I plus C2I squared. This is another and whole mod M. So that means here I value will be 0, 2, 1, 2 dot dot n minus 1. So in that case, we will be using same process, almost same process. That process what will be the changing of I will be faster. So jumping will be from here to here maybe quickly, or here to here is quickly. So in case of very large data set, we use quadratic probing. That means the probing method is a quadratic function in terms of I. Okay, and then we do the same process. So this is another kind of like linear probing. Quadratic probing is another kind of open addressing for collision resolving, and there is also we can say double hashing. Double hashing means using double hash method. Okay, so instead of using one single hash method, we can use double, multiple, or more than one hash function. So here you see that our hash function, this is h1k, this is a one hash function, and h2k I into h2k, this is another hash function. Maybe the first hash function will be, it is upon you or us how we will use this hash function. Maybe it may be like this, h of ki equal to, so first one I may say say maybe 2k plus 1, okay, plus I into k plus 1, and then whole mod M. Here I value equal to 0 to M minus 1. So the change is change here is a double hash method, hash function. It is called double hashing. And the process is same. Whatever and now whatever hash function we use, it is up to us, or it is based on our data set given. So now everybody, so speak up. Now do you understand what is called linear hashing, what is called quadratic hashing, and what is called double hashing? So in a linear hashing, we will use a simple hash function. Okay, and then to detect or to resolve collision, we will be using a simple increment, linear increment of probing values, I index values. For double hashing, we will use the two hash function. We will use two different hash functions. Okay, and for quadratic hashing, we use a quadratic function over here. Why do you use this quadratic function? So that it becomes faster, jumping becomes faster. It's a large jump. Does anyone has any question?
I have a question about the assignment, not about this though.
Okay. What is the question?
I was just wondering if you could show us how to get started. It's really confusing.
For the assignment?
Yeah.
I will ask our GTA to have a complete session. Okay, then you can join with him.
Okay.
That may work if we can get more time to our GTA, because I have a few more minutes left and I have to cover this topic today. So assignments, which assignment is due?
The heaps.
Heaps, right?
Correct.
Okay. Let me finish my topic, then I will see that if I get time, then I will come back, or I will ask our GTA to discuss the assignment.
Sounds good.
Okay, thank you. Please send me an email, okay? Send me an email and also copy the email to our GTA. And then maybe tonight today he has a session, right? Today or tomorrow. Okay, if needed, I will extend it for a few days, okay? The assignment.
All right, thank you.
Okay. So now this is a data set. For instance, this is a data set 14, 17, 24, 37, 34, 16, 26. And we have two hash function. M is given 11. Okay, a hash function 1, h1, hx or hx equal to x mod 11 and h2 equal to x mod 7 plus 1. There are two hash functions. Okay, so it's double hashing. Okay, the slides are given over here. Okay, so you can so now you see that if we want to solve this problem, sorry. Okay, so this one is we want to solve. Okay, so here, okay, so 14 mod 11. Okay, then h1x first of all we will use h1x first is 3, right? So then we got 3 and then this is table. So instead of writing table over here, so they put this is table. This is table. Okay, so they did not put like this. Just they put index, and then, for instance, this is table. Hash table. Okay, like this. Okay. So 14 mod 11 equal to 3. So then 14 is comes here. Okay, and it does not need to go to the next one. Why? Because we already got a empty space. Okay, and then 17 mod 11 equal to 6. So 17 will come over here. 25 mod 11 equal to 3. So now see 3, right? 3. And then since this position is already occupied, so then this technique is there. So our hash function, original hash function is h of k I equal to h k plus I is to k. Okay, mod m. Okay, so this position is occupied. Okay, so then we will use the next h2k. Okay, this one is 2k. So h2k equal to, so we said that x mod 7. So x mod 7, 25 mod 7 plus 1 equal to 5. So then what is the 25 position will be this 3, sum of this 3 plus 5. And then 3 plus 5 equal to 8, right? Equal to, so actual position will be 8. So this position will be, so plus 3, 8. So it's 8 position, 25. 25 is coming is position 8, because then probe value equal to 2, right? So the probe value, if we get it first time, then probe value equal to 1. Two different people use two different techniques. For instance, if you get it first time, you can say probe value equal to 0. If you say this one prob value equal to 0, 0, then prob value this will be 1. Or if you say this one 1, then this will be 2. What is your the starting prob? So for the first chance, if you say first chance, I got the position for the first chance, then we can say prob value either 0 or 1. If we say 1, so then the second try, you can say prob value equal to for this one equal to 2. So the prob value, so the authors to authors, this value differ. Some people start from 0, some people start from 1. But it is same thing, okay? So here you understand why 25 is getting this position 8. Is in the past using first this one, first hash function it got 3, and then in the second hash function it got 5. And 3 plus 5 equal to 8. So that 25 is taking position 8. And then now for 37 is modulus 11 equal to 4. So 37 will take position at 4. Okay. And then wherever it reaches 26 modulus 11 equal to 4. Then this, so 4 is already occupied. So then it will be using next hash function, this one. Okay, with I equal to first time 1. So initial value, say prob value I equal to 1, then say I equal to 1 plus 25, this one. What is this one? 26 mod 7 plus 1 equal to 6. Then then actually over here it will be 5, 4 plus 6, 10. 4 will be over here. 4 plus 6 equal to 10. So then 26 is taking position at 10. Okay, and in some case, for instance, even if we say this position is already occupied, okay, then what is the next step? Because then we have our I value equal to 0 to less than m minus 1, right? 10, right? So then in the next phase, even if we find this space not available, then we will say increase I equal to 2. Okay, that means 4 plus 2 times 6. 2 times 6, 12. 12 plus 4, 16. 16 modulus 11 equal to 5. And that maybe in that case it is getting 5. 5 is empty. If it's not empty, then we use I equal to 3. And then if we give more try, then prob value will be increasing. Prob value will be increasing. And in this way, this is the way that how a hash table, this is our hash table. Hash table. So a hash table is a linear array. So every entry, you see that it has its unique position, unique value, index value in the unique position. So it is easy to retrieve or search an item, okay, in constant time, because whatever we will, so using this for index 4, okay, this index 4 is generated from the key value, right? So then we know that we can retrieve in reverse order. We can find this value at index 4, we get 37. And index 4, index 6, we got 17, index 8, we got 25. So we are getting constant time. So for some cases, if probes values is there are some additional probe values, then we may need to jump 1 or 2 or 3, a few more jumps. But compared to the probe values is less than m. So compared to the jump, compared to our data set, probe value will be minimal. So that means still we will get a constant. Now, the question is that, for instance, let me open another slide. Give me 1 more second, please. Nine, 4. Stop. So hash table, right? So hash table, how do we find an element with its key value, right? So then hash index key is generated lighting this hash table. And the question is that so far that we discussed that hash value with numeric numbers, with key value numeric numbers, right? Now, for instance, if you are given a data set like this, the question is that can we generate hash table with this kind of data, non-numeric data, like a string data? Yes, we know that we can generate for each character in a string. There is a ASCII code, right? There is a corresponding ASCII code. So if we search for ASCII table, ASCII means American Standard Code for Information Interchange. Whatever character we type in any language, internally these are converted into an ASCII chart. So in an ASCII chart, all characters and all numbers have a unique code. For instance, capital A and uppercase A. So uppercase A is 65, its position is 65, decimal number 65, B is 66, okay, and the lowercase a is 97, lowercase b is 98. So all character. So you may hear Unicode, right? Unicode is ASCII code is 7-bit, 0 to 127. Extended ASCII code is 8-bit, 0 to 255. Okay, and for every character it has a corresponding code. So using ASCII code, if we are given a non-numeric data key values, so we can use some formula to convert this character to a corresponding integer number. Okay, and then later we got integer number. We use that number to use our hash function. So for instance, let us say for any number, for instance, term, if you generate maybe by adding, you can do by putting the ASCII code one after another, okay, or any formula that you use, same formula you use. For instance, you got for term this code, and this term will be generated by a hash function. Hash function may be a simple modulus function, and then you can do it. Okay, and then for instance, term is using hash code, hash function. We got index 2, so then in that index 2, in the hash table in the index 2, we'll put term. And for dict, it will get hash code 14.4, then we had dict will be over here, and similarly it will go. Okay, so as long as you select a good m, what is m? M is the nearest largest prime number, then hopefully we will get a good hash table. Like this way, for every Sam got is index 0 and Sam is 40. This is our hash table, and this is our original name. For instance, in a dictionary or a telephone book, regular telephone book. Okay, so like 20 years ago, 30 years ago, people did have telephone book. Okay, so now we don't see any analog telephone book, maybe yellow page, they don't supply it. So the telephone book, it would have all telephone numbers, maybe serially by the owner's name. Now they come serially, but here in the hash table, the keys do not come serially, do not come alphabetic order. It come in the order of index value that generate. Index value. Okay, this is the main difference between an ordinary table and a hash table. Okay. So that's now for this chapter. Okay. And oh, sorry, I wanted to come back to, give me 2 more minutes, please. I wanted to come back to the our slides. Now I discuss everything from other slides, so whatever will be, but with some simple examples. Okay, we discuss open addressing with 3 examples, with simple examples. Now, if you read the book, the book has like, it's an old book, so it has like old kind of examples. For instance, how do you put telephone numbers or something like this in a hash table. So now, if you go to the slides, maybe you will see what is easily understand. Okay, now go to the slides. So if you do not find anything readable or easy, so let me know. Okay, if you don't understand anything. So now we discuss this. Now we go to slides. The book has this description with simple. So we discussed quadratic probing, and then one thing, remember that the hash function, what will be the hash function? It's upon you. Okay, even you will be given a hash function. In my test, I will be given a hash function and a set of numbers like this. For instance, as we discussed in our last lecture, I will give a hash function like this, and I will give a hash table like this, and I will ask you to generate a hash table like this, and number of probes. So practice this one, okay? If you understand this one, then you will be able to do that test question. So these are from numbers, characters are converted to ASCII code, and then are converted to decimal number. Then whenever you get decimal number, then you can use to arithmetic modulus operation. So there are many techniques that can be used. Okay. Okay. So the hash function aim is to improve the performance from big O n or log n to constant time, big O 1. Yeah. Give me a minute, please. Let me get my attendance today. Okay, please respond to the attendance. And Jason. Matthew. Daniel.
I'm sorry, Jason's here.
Jason is here.
Yeah, Jason's here.
Matthew. Daniel. Myers.
Here.
Antonio.
Here.
Jasmine. Terton. Elisa.
Here.
Tyler. Ernest. Angel,
Here.
Jaden,
Here.
Cody, Isaiah,
Here.
Jimmy,
Here.
Savvy,
Here.
Loyal, Dave,
Here.
Karen, Mikhail,
Here.
Zest, James,
Here. And line 10 is also here.
19, Dave,
10.
Tyler.
Yeah.
Also, line 21 is here as well.
21.
Yep.
Yeah, 21. Mikhail is here.
Yeah. You didn't mark it.
Jess, James,
Here.
Brandon,
Here.
Noah, Alan, Kenya,
Here.
Jimmy, Lilivia,
Here.
Jesus, Cameron, Sebastian,
Here.
Alice,
Here.
Justin, Daniel, Andrew,
Here.
Nicholas,
Here.
Jessica. Okay, is anyone left? Okay, thank you so much, and you have a good day.